Okay, welcome back to machine learning. And we're finally getting to the good stuff, I'd say. And in particular, today we cover neural networks. And I suspect many of you have heard this word before. And today, hopefully, you'll know what this word means, like formally in some way. Okay, the one thing I wanted to mention is that neural networks are very, very popular, as you might know. And for this reason, there's an unbelievable amount of resources out there to learn neural networks. And so you shouldn't be surprised that there's people out there that do potentially a much better job than I do at explaining these things. So there's lots of videos and stuff, and there's like one particular person on YouTube that I think does a really good job of describing these things, and there's other ones too. But anyways, I thought I should share this because like he's put in a lot of time. And yeah, so anyways, on the course website, under this lecture 22 part, there's like a link to this like YouTube video series which covers neural networks in like a nice visual, kind of maybe high level with some details similar to what we do in this course, like in this lecture, and then like some other stuff afterwards. And it also covers some intro to language models, which we'll do next class as well. Anyways, just thought if you want to watch some fun YouTube videos about this stuff too. And then there's like way more other resources online about this stuff. Okay, so our goal for today is going to be to learn about these neural networks. So I'm not going to go over anything from the last classes, really. I'm just going to start straight into neural networks. There's quite a few things to cover. And the way we're going to do this is I'm going to really like aim to kind of motivate this with like some intuition and high level stuff, and then slowly get into the maths. And we're not going to work, there's not going to be too much math details as opposed to like trying to understand what these things are, why they're interesting and stuff like that. And that'll be the point of, that's how we're going to cover neural networks in this course. And then in other courses, you go into like many more lectures of actually deriving calculations and so on and so on. But hopefully after today, you'll understand what all those calculations and stuff are. Yeah. Okay, well, hopefully the mic will do that for me. Is this better? Okay, cool. So yes, so I start with the first slide being this like high level, very simple story of what neural networks are. And given everything we've built up to so far, it should be very nicely positioned to describe this. So a neural network is just a function, okay? And in particular, the way it's used is it's used as a predictor. So it's exactly this like function that takes in a feature input and is going to output whatever you're trying to predict, like probabilities, house price, or whatever. So literally, it is just a function. And you could summarize what today's lecture is all going to be about is just defining what the function is. And then like talking about what it looks like, why it's interesting, how you can think about it, and so on. But it's just going to be this function. Okay. And there is this classic visual representation to describe it because the equations kind of get messy. So you always think about it with this visual way. And I just give you the high level picture, and we're going to go into the details much later on. Okay. So you think of the left side as being the input feature x. Right here, I've just broken up x into like its components. So here we would have a dimension of 3. So this is the case where d equals 3. And we've seen this, right? This is like x0, x1, x2, x3. I've just written the vector out in this like nice column way. And then there's some things that like, there's these arrows, we're going to talk about them. There's these things in here that are called neurons. And this is like a layer of the neural network, and then it propagates. So you should think of information as going from left to right. It's going to propagate some information to here and then to here. And then eventually it's going to get to the very end on the right. And then it's going to output something, which is like what the function outputs. So this is the output of the function, this A3. Okay. And this is a very specific neural network. It turns out these things could have many more of these kind of layers. You could like keep stacking these together. You could have many more of these neurons. So these could be like, you could add more of these circles and so on. We're going to talk about all this. But you should really just think about it as this thing that takes in an input, does some processing in the middle, and then outputs something, just like we've seen any function do before. Okay. Why are these like function? What are we going to do with? I just defined a function for you. What are we going to do with it? Well, we're going to do what we have always done with predictors in this class, which is we're going to try to learn the best predictor in this class of predictors, or the best function in this function class. And so this is like the high level story of what all that's changed is that if you want to do ERM, and we've seen in this class that like even for classification, you could think of all the problems as just doing ERM for a regression problem. Okay. And so the setting is just this. You have a data set. You want to output this ERM, like the ERM learner outputs this predictor. It's just the arg min, right? The minimum function, the minimum predictor that minimizes this estimated loss. That's all we've like really ever wanted to do with this ERM stuff. And then all that we're going to change here now is that the function class is not going to be these linear functions. It's not going to be these polynomials or these sigmoids. It's now just the set of functions that are neural networks. So this is going to contain functions, and this function is a neural network. And then it's going to turn out, just as all the other functions we've seen, that these functions can be described by some set of weights. And there's going to be a lot of weights. There's going to be these weight matrices. But all that a matrix is, you can think of it as just stacking a bunch of weight vectors as rows. So it's just like a nice, convenient way to represent weight vectors. Anyways, there's a lot of these weights. And guess what? If you describe a function by its weights, then you can do optimization over its weights. You just do gradient descent, and you're done. And that's literally it. And this gradient descent with neural networks, that's called backpropagation. So it's everything we've seen in class. OK. So for the rest of the class, we really focus on defining what is this function. And we don't actually derive what the gradients are, because that'd be a long set of calculations, but really it is just taking derivatives. OK, so let's begin. So it turns out everything we've seen we can think of as neural networks for the most part, like all the functions we've seen so far. So we're going to step through that kind of analysis, I guess, first. Oh, so there's like a question that is maybe it's an interesting question. The question is like, how are neural networks different from normal machine learning? And I think this question is like it's like a syntax error or something. Like this question doesn't really mean anything. Like machine learning is like this whole topic of like learning a good predictor. A neural network is just a function class you choose to solve like the machine learning problem. They're like, machine learning is the whole field of solving, like of learning a good predictor. Neural networks are just a function. They're like, they're like different, completely different kind of words. Okay. And I mean, you use the neural networks in machine learning, I should say. Okay. So now we look at previous functions, so previously seen functions, and we think of them as neural networks. So that's how we're going to build up our intuition. Linear functions, the first ones we started with, there were these functions that just look like this dot product, feature vector times weight vector. Turns out this is a neural network of like a certain type of neural network. And in particular, this is what the neural network would look like. So it has this input x, right? This is the feature vector. And then it has this output. This is the thing on the right. And you can see there's none of these layers in the middle in this case. And the way, like, what you would write is that this A thing, well, since f of, as I've defined this neural network, the output of the neural network is A. It's the thing on the very right. So what should A be? Well, A should be exactly this thing, this X transpose W. But I want to write it out like explicitly just so you see how these like connections and so on work. So this thing explicitly would look like x0, right, times w0 plus x1 times w1 plus x2 times w2 plus x3 times w3. Okay, that's the explicit thing. But like, turns out that this has like a nice visual understanding from this picture on the left. So you could think of each one of these features, right? So this is the feature vector containing features. Each one of these features is then multiplied by the weight, right? So these lines represent weights. These represent what are called neurons, but they're going to just be like, really, you can think of these features in this case. So it's like feature times weight plus feature times weight plus feature times weight. So this A thing, this A neuron is doing this operation of summing up all of these things. Okay, just taking in all these things here and summing them up. Okay, and I'm going to write this one more way, which will become apparent why I'm doing this, is you could think of this whole thing as a function h, and we'll see what this h is later, applied on this linear function. And in this case, h is just like the identity function. It's the function that literally just, as we've seen, just outputs this. So it does nothing. But the point is I can wrap this around in some function h. We're going to see that h can change in just a second. But these are equivalent, like if h is just this identity, it's called an identity function. It just outputs what it inputs. Okay, so that's what you can think of this A is doing this operation of taking this dot product and then applying a function h. In this case, it's the identity. Okay. Another example we've seen, the sigmoid. We can think of this as well as a neural network. The sigmoid function, right, is just like sigmoid applied to whatever. And this is this, now we need this to be the A for the neural network. So like, what does A become? It's, as we said, it's like this sigmoid. But if we explicitly write it out, we can see it really looks like this function H applied to this dot product. So you can think of this as some function H being applied to a dot product. Okay, and in this case, H equals to the sigmoid. Okay, so you can think of this like A, and this thing is called an A neuron, whatever this neuron. What this neuron is doing is it's doing this computation of dot product and then apply a function H on the dot product. So yeah, so you can think of the past two, like these two functions, the linear and sigmoid functions, as these very simple looking neural networks. You're going to see that this trend of taking dot products and then just applying a function is all that a neural network is going to be doing. Okay. We've seen one more type of function, right, which is like this polynomial features function thing. And here's the way to kind of think about these polynomial features in neural network land and kind of what they're doing. So what did this polynomial features thing look like? It used to look like, you know, you have some function that is the dot product of this feature function applied to the original features, right? So this is like the polynomial feature function applied to the original features, dot producted with the weights. We've seen this. And so that's your polynomial function. And the way to think of this is that you started with some original features, x. You then applied this function here. And notice how I haven't drawn these like these lines and stuff like that, because you actually can't represent this as a neural network, it turns out. But, sorry, just to be clear, I said the word cannot. This cannot be represented. So you start with this set of features. You think of this phi of p as making the features bigger, right? So it's just this map that makes you makes a way bigger new feature that you got from x. So this whole thing here now is phi of p of x, right? Okay, so you got this very big new feature, and then what you did is you just did a linear function on that new feature, and then you would get a here. So a would be this thing here. Okay. So here is like the kind of important insight to give you some motivation of why you would want to use a different function at this point. Okay. Because so far I told you there's this thing called the neural network. I've told you, okay, we've seen these other functions in this course, but at this point you probably shouldn't see any motivation to use a different function. Like we've seen that if you use neural networks, if you increase p, you can just like represent very, very complicated things. So why don't we just do that, right? Like why do we really need a different function? Okay. And so here's kind of the reason. What you will notice is that, okay, at the end of the day, there's some relationship, right, between these input features and what the output ends up looking like. And we said, why would we introduce this like polynomial feature map? One reason was like, oh, maybe the relationship is this like quadratic relationship or something. Maybe you really need to square the input, and then you can multiply it by some number, and you get what the trend looks like in the output. But what we didn't know is like what exactly is that relationship should be. Like what should we square it? Maybe we should cube it, or maybe it needs to be to the power of 9 or something. And so what we did is we like naively said, okay, let's just introduce this new feature that has like every possible combination of like x1 and x1 squared and x2 to the like all these second degree polynomial terms and third degree and 4 and so on. Okay. And many of these might not be useful, is the point of the story. It's like, maybe you really only need this term, but you didn't need all of these. And you're like wastefully introduced all these. And when you make p very, very large, there's going to be a lot of new features. And many of them might be completely useless to you. You might really only need, like, let's say x1 to the 9, but you introduce like thousands of other completely unnecessary features. So this is kind of the big observation of what's going to be the difference. So many of these new features introduced by like the polynomial, so in this polynomial feature, may not be useful. This is kind of a, because we just naively picked some degree p and like tried every possible combination of x1 times x2, whatever, to that power. And in particular, when p is large, this is very wasteful. Okay, so the natural thing that you'd want to do is, instead of naively guessing what features you need, why don't you learn what the features are? So why don't we take as input the original features and decide what features we should pick here? Instead of creating all of them, right? Why don't we just actually learn which ones should be here? Okay, this is going to be kind of the big insight of what the neural networks are really doing, is why I'm spending quite a bit of time emphasizing this. Okay, so now I'm going to go into talking about neural networks and how to think about them and interpreting them and so on. Okay, so first, some terminology of these neural networks. So I've already said some of these things, but if we look at the neural network I originally presented, and I'm going to slowly kind of introduce the math and the terminology through this lecture. So what we call each one of these kind of vertical things is a layer. So this is called layer 0. This is your input. This is layer 1, 2, 3. You can have as many layers as you want. That's just a different neural network. And that's going to be something we're going to see in a second called the neural network architecture. So the number of layers is a different neural network architecture. In each layer, you can have a different amount of these neurons, and we're going to talk about that in a bit. But yeah, so here you would have 3 of these things called neurons. So these circles, these are called neurons. Okay. And then these lines, as we've seen, are called the weights. So one line is one weight, it's just one number. Okay. And so yeah, this is all I want to say about this on this slide, is that you have these neurons which store the original feature information. They're then going to use these weights in some way, and they're going to propagate information to the right. And these neurons are now going to store some new information about the original features multiplied by these weights. And then from here, you're going to propagate that information again to the right. That's going to store some other type of information. And then you're finally going to get to this output. Okay, that's all I want to say for now. So that's so okay. So now to understand what is this kind of information that you might imagine storing, and how might it change through the layers and so on, we cover 2 kind of classic examples. One is the regression case. What might this look like? What might a neural network learn after it's been optimized over? And what might it look like for a classification case? Okay. So first, for the regression case, and I'm going to build this example up as kind of what you as a human might think to learn, if you were to manually kind of write this out, and then you'll see how this relates to the neural network. Okay, so imagine you're in this regression setting, and so your Y, your labels are just the real numbers. They're going to represent house prices. And your input is this feature vector, the feature vector we've always seen, this set of features. And let's just say the dimension is 3. So clearly, so this is our input. This X feature is our input. We write it out as we've seen with neural networks. You have these 4 neurons. There's this 0 neuron, which is this bias term. Okay. So I'm going to, since this is an example, I give a very specific interpretation to each one of the features. X1 will represent the number of rooms. Right? X2 represents the number of floors in your house. X3 is going to represent the crime rate of where that house is located, let's say, or something like that. Okay. So here is kind of the high-level intuition of what might happen. So maybe you as a human, you look at this stuff and you're trying to predict house prices. So maybe you're going to first look at some of this information, such as the crime rate, right? And then you're going to decide, okay, this kind of gives me some understanding of what is the quality of the school, maybe. Or sorry, what's the quality of schools around this house and something like this. Maybe that'll make a big difference for your, okay, so let me write this as a node. So I write this new neuron, which is going to be this A2, okay, I don't even fill it in. And you might think of this as the school's quality nearby. So this gives you some new information. So from, and I'm going to write this as a node. So from this guy, you can infer some new kind of information. Okay, this only used one of the features. Another piece of information is maybe you can infer the size of the family that lived in that house or something. And how would you do that? Maybe you would look at the number of rooms in that house. Yeah, maybe you'll look at the number of rooms in that house and the number of floors. And maybe this will give you information about something like the family size. Maybe let me write this up here so I don't take up some space in a second. Okay. And then maybe from these two things, and this is kind of, once again, maybe a little bit of a hand-wavy example, but from these two things, you can then use these two kind of features, these new features or this new information, to then make your prediction about actually what is the price. So this would finally be your output, which is like the price of the house. Okay. So this is kind of an example of how the information will flow from here to here. And then you get like some new, you store the information as some new representation or some like kind of new features. And then from there, you then predict your house price. Okay. What's happening with the neural network is we don't know like which like information should this neuron look at before. In this case, like we said as humans, maybe for this one, we'll only look at these two things. And for this one, we'll look at this. So what we do is we define the neural network to have the possibility to look at everything. So I'm going to define these lines in a second. And then the goal of the neural network is going to be to learn which things should it look at. And so, for instance, it would set like these. Okay, so let me write the weights now, and I'll write them as these like dotted lines, maybe. So you would actually give the the neural network all these connections. And then to make the notation the same as before, this would be called like A1, 1, A1, 2. And there would be this like bias guy as well. Equal to 1. Okay. So you give the neural network all of these connections. And the goal of like when you do this optimization and when your learner decides on what neural network it should output as the best predictor, is it should then decide that this weight is pretty unimportant. So it should probably set this weight to like 0, and maybe this weight to 0, and this weight to 0. But these bolded ones, these are like the important ones. So it should set these weights to like some large number. Okay, so this is like an example of kind of trying to interpret what might like your learner output in terms of the neural network. Like it might decide that this is the values of the weights it should pick, right? Because at the end of the day, what does it mean for your learner to decide what neural network or what predictor it's going to output? Well, that means it's going to pick some set of weights, which then defines your neural network, and that's the thing you're going to output. Okay, so this is like one way to interpret this thing, and I write the last thing here. Okay, and then I give another example in a second with the classification case, which I think is probably more like intuitive of how this works. Yeah. Yeah, so once again, I think this is a slightly imperfect example, but the idea is that like this stuff is kind of like very raw information. It's just like number of room. These are very, and maybe these numbers aren't like the best thing to use to predict the price of something. So maybe what you'll want is to like take this kind of information and store it in some new representation, some new like feature, which is like the family size. And the claim is here that family size, this kind of information is much more useful for predicting the price of a house for some reason, or the school quality, than these raw numbers here. And once again, this is maybe a little bit imperfect. I do believe the next example will make this much more clear how what you start with some very, very raw data, and then you like you choose some better and better representations such that at the end here, you have some very useful features for predicting the thing you really want. Yeah. Yes. This will be some, so like, just to know, like this word hyperparameter, maybe we haven't used as much in this course, but the idea of a hyperparameter is like, when we talked about this model selection, model evaluation, whatever business, there we said, okay, we might not know what, like, let's say like function class to choose, right, for our learner, or we don't know what step size to use for our learner. So what you do is you train multiple learners, each with a different function class or a different step size, and then you would plot the test error and pick the learner that outputted the best predictor for that corresponding thing. And here, what we're going to see is that you can, so choosing the number of layers or the number of neurons in a layer and stuff are all things that you don't know beforehand. So what you really do is you train one learner with a neural network function class that has, let's say, 2 layers, and another learner that uses a neural network function class that has 3 layers, and so on and so on. And this is kind of what happens in Fractal. You just search over these things with kind of arbitrarily, and then you like have a learner that outputs a predictor for each of these cases, and then you plot the test loss and then pick the one that's kind of the best. And these things, like these parameters that you train different learners for, these are called hyperparameters. Yeah.
So the way that these engineers work is they do like intermediate, like they calculate other features based on the boundary now, right?
Yes, this is how you can think about it. We're going to see it even more clearly in the next example, where like you start with these very raw features, then you get like better features, and then you're going to see with more layers, you're going to get better and better and better features.
Also, the machine learning that we've been doing before, couldn't be thought of as just like a neural network with just like one layer, which directly goes to unity?
Yes, that's right. So that's what this example above was saying. So these examples were saying what we've been doing before is we've had this input, and it just took one feature. It never learned any new features. It just directly only used the raw input, the raw feature we got, and immediately mapped that to some prediction, always using a linear function and then some other function potentially applied on top of it. That's all we've ever done so far. And here we're saying maybe we can learn some intermediate representations along the way. So like you start with some feature, you apply something here. We're going to talk about how this looks. You get some new representation, new features. Then from those features, we're going to see, yeah. So maybe I move on with this, I think, better example next. So this is a very classic way to, this next one with classification is like the classic way to talk about what are neural networks like learning inside, or what does this representations mean. And this is classification. And here you'll see either like cats versus no cat classification, or like handwritten digit classification. So I chose the like cat versus no cat one. Okay, so you're trying to classify whether your picture has a cat or no cat. So there's a 0 or a 1. And really what we're going to end up doing is we're going to want to just do what we've learned in classification beforehand, which is you're going to predict the probability of there being a cat. And then once you do that, which is what this whole function is going to do, this neural network is going to predict the probability of there being a cat or not. From that, you can just classify whether it's a cat or not if like that probability is larger than 50%, let's say. Okay, so really our goal is going to be to predict whether, like predict the probability of this being a cat or not. Okay. How do we set up this problem? And here I do this a little more explicitly, which is like our input is a picture, but like we always set our inputs is a vector x. And here I explicitly explain how you would do this. So a picture is like just a set of pixels, right? So you have all these pixels. And then you have another row all the way up to here. And then you go all the way down. There's all these pixels, right? And we're going to pretend like this picture is just black and white. Okay, so each pixel is just going to have, let's say, some numeric number, like some real number. Well, it's going to be an integer that describes how intense is that pixel. And once you know the intensity of every pixel, you know exactly what your picture is. So here I'm just going to make like some assumption of the size of the picture. And it's going to be a very small resolution picture. It's going to be 16 by 16. So how many pixels do we have? We're going to have 16 by 16, which is 256 pixels. And this is going to be equal to the dimension d. But once again, we need this vector, right? Like we always have been working with our inputs as being feature vectors. So what you do is you just basically represent this giant like picture or array of things as just a vector. And how you do this is you take, let's say, one way to do this is you take the first row, and then you put it as like the first few elements of the vector. You take the second row and just concatenate it under, and so on and so on. So you end up with this vector like this. So this guy's going to be your x. And you're going to have a bias term at the beginning as before. So you have this one guy here. And then you're going to have like x1, x2, all the way up to all of these x256. And these x1 to x256 represent the pixel value, right? How bright is that pixel? So hopefully you can agree that this vector just carries the exact same amount of information as this picture. And it's exactly the picture. You can just decode it, like put them back into this square format, and you get the picture back. So now we have our input thing, and you can really think of x as now a picture. Okay, so our goal is to predict what is the probability that this picture is a cat. So the claim is that this neural network function is going to take as input this picture, and it's going to output a probability. That probability is this final neuron here, this A3. How can we think, like, how can we interpret what the neural network is doing inside? And this is the interpretation you'll have. So you start with this input, the picture, right? This is your x. And then notice that each one, okay, so the important thing, let's just take a slight jump back to this picture here. Some things I wanted to highlight. Every single neuron, right, or well, I should say every single neuron like in here has a connection to every neuron in the past. So there is this connection of these weights from every neuron in the past. Similarly, if you go to the next layer, every single one here. Except for the bias. The bias, the bias is not like some linear function. This is just a number so that you can offset this thing. It's the same way we thought of the bias before. So every neuron, except for the bias terms, are always connected to all of the past neurons. Right? Each one of these, like you can think of each one of these as having its own weight vector. That weight vector would store all these connections of everything from the past. Okay. And some other notation stuff is this superscript is denoting the layer. So these things match. Back to the cat picture thing. So just so this neural network doesn't look so scary. All that I've done is I've drawn a neural network now with the same layers as we saw above. There's 0, 1, 2, 3 layers here. Now I've written it in this more general case. So now we have like 256 neurons. So I wasn't going to draw 256 circles, right? So I've written ... Then it goes to some new neurons here. Here, I also written in this general case. Here, there's much more than 2 or 3 neurons. There's this d to the 1 number of neurons. Okay. So in particular, I can write this whole layer here as a vector. I'll call it A1. And the thing I want to highlight is that this thing is an element of R of d to the 1 plus 1. Okay, so point is there's this many neurons in this layer. And then similar for this here. You'd have this A2 vector, and this would be an element of R d to the 2, which is the dimension of the second layer, plus 1. So now what's actually like, how can you interpret the inside of this network? Well, it takes in this picture, and then let's look at just this neuron. This neuron is looking at every other neuron from before, right? All of these. So it'd have like 257 connections, right, from all the neurons from before. And you can think of like, when is this neuron going to be, let's say, like a large number? And what you might find is when you look inside, and by look inside, I mean you look at which values of x cause for this to be a large positive number, and then you remap those values of x to a picture, you might find something like this. And this is actually what ends up happening if you look inside and try to do it. So I'm redrawing x as a picture now. And what you would find is that this neuron is only a large positive number, or like something non-zero, only when this part of the picture, let's say, has some values to it, or like there's an edge there. You can interpret this as this neuron is detecting kind of like the top of this cat. Okay, so from raw pixel values, this kind of neuron is understanding something more, let's say, abstract, which is like that there is some like edge going on here, that there's that this is the top of the cat. You can think of all the other neurons inside as doing some sort of like similar thing, and we'll do another interpretation of this lower one here. So you can think of this guy down here as potentially maybe recognizing the lower part, like the belly of the cat, let's say here. So this neuron is only non-zero, let's say, when there's like an edge there. Okay, so the claim here is that these features are now somehow like more useful than the original just underlying pixel values, which is very hard to interpret. Okay, but we're not done there. We take these features and we're going to somehow create even better features from them, which is we're going to move on to the next layer here. So let's look at what this neuron might learn. This neuron, once again, is taking information of all these other neurons. We're thinking of these neurons as kind of all detecting different parts of different edges in the picture, right? So what might be an example of what this learns? And an example is going to be something even more kind of like useful or abstract or something. Well, not abstract, but like some more high-level concept. And this one maybe learns like it's a non-zero value when it sees a face of a cat in this area, let's say. Okay, or maybe just like a face in general. So this is clearly much more useful information than like, once again, these underlying raw pixel values. And you can think of this feature here as learning something also very high level and useful. For instance, maybe it's only non-zero when it sees the body of a cat. Okay. So now the claim is, okay, now we've gotten these much better features, and we've somehow picked them out. This is what the learning process, when our learner will output a good predictor, this is what we're interpreting a good predictor to be. It's a predictor that can take the raw features, get better features, get even better features, and then use these much more useful features to then predict like the actual probability of seeing a cat, right? So that's what this A3 is, the probability of that being a cat. Okay, so this is potentially like the most kind of like intuitive and useful picture to understand of what these neural networks are doing underneath. This flow of information, of like getting better and better information. If you make them deeper and deeper, you're going to find out that you're going to get more and more powerful functions. It's kind of like increasing P of your polynomials. If you added like 10 or 20 or 30 layers, you're going to find that there's going to be very, like, the features are going to get more and more like elaborate and interesting and so on. And you can predict even more and more complicated things, or like more precisely. And in contrast to these polynomial functions and polynomial features, notice how these neurons, these features, are being learned from this input. You change the weight, and what I mean by learn, like you change the weights, like the value of the weight on each one of these edges, you will get a different value for this neuron. Okay, so like depending on what the input, like what your data is, you can learn different kind of features. But in the polynomial, these are just hard coded. This is always would be something like this thing times, let's say this edge, like let's say x0 times x1, or it would be like x1 times x1, so that was x1 squared and so on. So we somehow like hard coded the features before. Now these features are being learned, and by learned, once again, it's the learner is optimizing this estimated loss, which will mean actually picking values of the weights here. Okay, I think next we're actually going to get into some math. Or like, I'm going to define the function mathematically now. Oh wow, there's quite a couple questions online I didn't see. Let me. So just a quick question, like the better features, would they reduce irreducible error? And to answer this, it's no. Like all we're doing is just using the input features in a better way. Like it allows you to have a more like it basically can do better than like if you have a polynomial of a very, very high P, then you can represent very complex functions. The claim is that you can have a neural network with much, much less weights, like much less weight vectors to represent the same complexity of a function. But at the end of the day, like you could always get a very, very complex function by making P very large. You can always get a very, very complex neural network by making the layers very, very large as well. So you're never like, to reduce the irreducible error, which is to answer that question, you would need to add completely new like input features. So that would mean like maybe increase the resolution. If you increase the resolution, you'd get new, like totally new input features. And from that, maybe you can make better predictions because you see like very fine-grained resolutions of things. And maybe to answer the other one, or something like saying like if P gets very, very large, a lot of the info gets useless. And the claim here is that this is exactly what the neural network is kind of addressing, is that it's only picking out the useful features when P is really, really high. Like when P is really high in the polynomials, you get a ton of features. And what you will find is that almost like very few of the weights actually end up being some non-zero value because many of the features are completely useless for your prediction. And what the claim here is that the neural network is not even wasting its time creating any of those features. It really only creates the useful ones. And someone, okay. Yeah, like maybe the last thing to answer is once again that this A3 is outputting a probability. So you're really here, you're solving, this is a way to solve the logistic regression problem, right? You're solving which is trying to predict the probability of 1. And all we've done is we've changed the function class from a sigmoid, and the sigmoid was really just this. Remember, the sigmoid was just this step. What we've done is we added all this pre-processing kind of stuff before that really created just better features that the sigmoid can use. And you'll find that this is actually just exactly like this sigmoid function here at the end. And all we've done is we're solving here the logistic regression problem with a different function class. And it's now the neural networks instead of the sigmoids. Okay. Yeah. Right. So yeah, like the question is kind of like how's the neural network going to tweak the weights or change the weights to achieve its goal and so on. And I give kind of like a high level thing because I guess we'll see some of the math details in a second. But remember, it's outputting this thing, and this is the output of the neural network. And that's a thing that's going to be used in the estimated loss. You're trying to minimize the estimated loss. That thing's going to be a function of what you predict, which is this output, and the true label. Right? That's what you have in your data set, the true label. And your goal is to somehow tweak set these weights, all these lines, like everywhere here, all these lines, set them to such a value that the prediction is good. And that will mean that you actually predict in that estimated loss, like your f of x actually predicts with very high probability that it's a 1 when it actually is a 1, and a 0 when it's a 0. So yeah, so the goal is kind of like through this estimated loss, but you interpret it as what does having a small estimated loss mean? It means that you're predicting the labels correctly. Okay. And so if you want to predict the labels correctly, you have to change your neural network's weights. And that's what the whole optimization process is doing. It's trying to pick what values of W should I set for these edges. And maybe let's make this more formal. So this thing obviously has like a definition other than this picture. But the picture allows you to like understand it, I guess, easier and stuff. So what is the definition? Like, what does it look like? Well, it looks like this giant kind of like iterative composition of one function applied to another function, applied to another function, and so on, which should make sense. Like you start from here, you then apply this, you then apply this, and then you get this. So there's going to be like this giant dependence of functions. Okay, so let's write down, like what I'm going to do now is I'm going to write down what is f of x. Okay, so that's what I'm trying to answer. What is f of x? And so we're going to start with x from here, and we're going to write down all these equations to the right until we get to here. Okay. So to begin, we need to know, like, let's just look at what is one of these, what is the value of one of these neurons? Okay, and this A thing turns out to have a name, and this is called an activation, and I'll write that in a second. Or in particular, like, what is this A1 vector? Okay, so this A1 vector, first of all, is just by definition from above, is a vector. It has these values in it. And it's all the values from the first layer. First layer, it has these 3 values. These are the indices for that layer. Okay, what are these values? So these values are called activations. And these activations, let's look at one of them. So like A1 of 1. Oh, one thing that's very important to point out is, once again, this first thing, this first index of the vector is just a bias term. So there's no definition for that other than it's always 1. Okay, so that's always going to be the case. So what is this like activation thing? Well, it turns out to be equal to something called an activation function applied to Z1. And this thing's going to be a linear function, and I'll define it in a second. Okay, so important terminology, each one of these is called an activation. This guy is called an activation function. One potential choice for this activation function is the sigmoid. We'll see some examples after, or like we'll talk about this term. Okay, there's another activation, this A12. Turns out this thing's exactly the same. Except now it's going to use Z2 here. And I'll define these Zs in a moment. Okay. So once again, I'm just trying to describe this specific network here. Exactly the one that has these 3 layers this way. It has 3 neurons in these layers and so on. So I'm going to do this definition first, and then I'll do the very general one right after. Okay, so all that's left is to define these Zs. And these Zs are just linear functions. And then we'll look at the picture to see how these equations make any sense. So what I mean is, okay, one terminology. So notice how this is called like A1 vector. This is A2. 2 relates to the layer. A1 for layer 1. It turns out to make the notation like synonymous or whatever, that it's useful to call the input feature X as A0, so that I can just always write A's. So we're going to think of all of these as like a vector of activations. So A0. So I'm going to use that to make the notation kind of look the same. So Z1 is going to be A0 transpose times, and this is the vector, times W1, 1. Okay? And then Z2, or Z1, 2, is equal to the same input transpose times W1, 2. Okay, what are all these things? What I've done so far is I've defined what these are equal to. What is their definition? It's as you might kind of expect. Like, let's look at what is the definition of A1, this activation. Well, first of all, it's going to have this dot product of the input feature, which is A0, dot producted with the weight vector, this weight vector here, W1. Right? Okay. So that's the Z's. The Z's are these dot products. So Z11 is the input, right? That's this thing, dot producted with the weight vector W1. Those are the blue lines. So Z's are always going to be these linear functions, these dot products. Okay. Then all that happens is that this activation or this neuron, what it does is then it all will apply some function on top of that dot product called an activation function, which is this H. So if we then just look at what is the definition of this, it's this two-step thing. It's H applied to this linear function. Okay. And that's always going to be how every single one of these activations is represented. Is just take in the dot product of the previous features with some weight vector, right? These are all these lines. And then apply this thing called an activation function. And then what do you get? You just get a number. Okay. It's going to be the same thing repeated for the other layers, and I will write those out in a second. And I want to write one more terminology. So these Z's also have a name. Okay, so first of all, activation. These are both activation functions, same function. And these Z's both also have a name. And these are called pre-activations, which kind of makes sense. They're the thing that are going into the activation function. Okay, yeah.
So W1, W2 are completely different?
Yes. Yes, there's absolutely no, these are completely different weight vectors. You should think of W1, this thing, as being, so first of all, the superscript. That's indicating these are the weight vectors used for layer 1. Subscripts are indicating which activation is it referring to. And these will actually all, so W11 will be the weight vector used by this activation. W1, for layer 1. 2 means it's going to be used for activation 2 for layer 1. So this activation uses W2. If you had many more activations, there's going to be many, many more weight vectors. And yeah, so these are the weight vectors for the first layer. There's a completely new set of weight vectors for the second layer, and for the third layer, and for the fourth one, and so on. There can be a lot of weight vectors. And we're going to look at all these dimensions after we go through this example. Because that's like kind of where everything gets a little bit messy. Is there's like these things get very large dimensions, and then you have to match things and so on. But even here, we can study the dimension of the different objects. So A0 is just the input feature. What is the dimension of this guy? The dimension is what we've always seen. It's R of D plus 1. There's these weight vectors, W1 and W2 for the first layer. What are their dimension? Well, same thing we've always seen, R of D plus 1, because it has to be a dot product with the input feature. Now it gets more interesting. What is the dimension of this feature? Or sorry, well, this activation vector. This activation vector is now of what dimension? Well, you can just look at it. It has 1, 2, 3 dimensions. And you can, write it like this, where there's 2 actual activations plus 1 for the bias. So there's a 3. Okay. All that's left is to use the same pattern to write out what this is and then what this is. And it's literally the exact same thing we've seen. It's just the same pattern repeated over and over again in these neural networks. Okay. So let's just do that. And I can quite literally do that by copying and pasting almost all this. And we can see what subscripts and superscript changes, which is, I guess, a pretty useful exercise. So erase all this terminology. Okay, so what changes? So I want to look at the activation for the second layer. So I'm going to change A1 to A2. Then the only thing that's changed is now we want the bias for the second layer. And here we also only have 3 neurons. So this is valid. It only goes up to 2. You could have more though in this layer. So I just have chosen these layers to both have 3. Very easily you could have 3 here and 4 here. There's nothing stopping you from doing that. Let me finish going through this and I'll answer the question. So what changes next? Well, okay, once again, superscript here will change to A2, same here. Then it turns out that the pre-activations, they're also going to change to 2. So everything's the same. And now these pre-activations are, so 2's here, indicating the layer. And then the only thing that changes after is now what's the input? Like what is it a linear function of? Let's go up here. What is this thing going to be like what's the linear function that it's taking as input? It's going to be a linear function of this vector dot producted with this weight vector, so the blue lines. Right? So this would be A1 with the W2 vector, and then indexed by 1 to refer to this activation here. And then it's going to apply this activation function on, well, that's what the activation function on top is. Okay, so I changed the input to be A1, and it's dot producted with W2, right? Interpreting this as the weight vector used for the second layer for the first activation, this first activation. And then I change this guy here to 2. And so you see really the only thing that's changing is just like the layer index. Especially, like in this case, it's especially clear that that's the only thing that's changing because they're literally the exact same amount of neurons in both the layers. And really the only difference in dimension is that this thing was d-dimensional, but this thing was like 2 in 2-dimensional. Okay, so I can write out the dimensions one more time, but they're almost identical. So now we want to know the dimension of W2, which are the 2 weight vectors at layer 2, and the corresponding new activation we made, which is A2. These weight vectors, what are they doing? These are dot producting with this feature. What is the dimension that these things have to take? Well, they should be the same dimension as this activation vector feature is doing. So what was that dimension? That dimension was 2 plus 1. So not d, but now 2 plus 1. And then this corresponding new feature is 2 plus 1 dimensional because it's the same dimension as the previous layer. Okay, maybe let me just finish this. And then we have one last neuron, which is the output neuron. And this also follows the exact same pattern, but there's just one of them. So this one's super straightforward. Here you will just have A of 3. It's just one number. It doesn't even need, it's not a vector. It's the activation function applied to a linear function. And that linear function we unsurprisingly label Z3. And that linear function is as you would expect. It's going to take as input, so it's going to be the dot product with the previous layer's activation vector, so A2, dot producted with this layer 3's weight vector, W3. And I think here, yeah, I called it W31. Okay, and yeah, to close, like, what are the dimensions? What are the new things we have here? The new things we have here is, okay, there's no W2 anymore. That weight vector still is this dimension because it's dot producting with the previous layer's activation vector. You can visually see that as well. Third layer clearly needs a weight vector that is of the same dimension as the previous layer. But the difference is that this new activation, the final activation, is of dimension 1. So it's just an R1, R. And that would be R3. Okay, so this is a pretty instructive example to see like what's going on. What I'm going to do next is now like step through the more general version of all what the neural network stuff looks like and whatnot. Yeah. Yeah, so what you're going to find is then like this, and you're going to see this, I guess you have to work through this in the next assignment, but you'll find that if you don't have activation functions, this thing becomes potentially not very interesting at all. In the sense that like, yeah, these activation, okay, maybe I just give it away. Like, I think this is very instructive. Like, if you remove the activation functions, what you'll find, and we'll see this in actually like 10 minutes, it'll be very clear. If you change the activation functions to just be these identity functions, so they do nothing, what you'll find is that this is a dot product, then applied to another dot product, applied to another dot product, and so on. And when you write this with matrices and stuff, you'll find that this is just equivalent to never having any of this here, and represent using this weight vector to represent what all these multiplied together. So you'll just end up with a linear function is the point of the story. You'll actually have gained absolutely nothing with having this neural network at all. It would just be a linear function with another linear function with another one, which turns out you can mathematically write equivalently as one linear function. And so you end up with just a linear function. So yeah, so you would have gained nothing. So these things really give what is called non-linearity. So this h function will be a non-linear function. It'll be something like an exponential or something nonlinear, and then that's what gives rise to a lot of this power of these neural networks, is that they can actually then represent very complicated looking functions. But if you chose h to be just the identity, you'd be back to the linear function case. Yeah, so a really common one is the sigmoid. You'll see in the assignment some other ones, and you have to decide whether any function from reals to reals is an activation, is what we're going to see. You can pick anything. There turns to be some useful ones in practice that are helpful for various reasons. We're not going to get into the details, but there's all sorts of, it's like a huge research field. All people use all sorts of different ones. Like, for instance, GPT-3, it used this activation called like this Gaussian error linear unit thing. It's called a GELU. Anyways, it's just like a function. And so like this is really like GPT, like all these language models and stuff are using neural networks, and they have some activation functions inside. And this is what the functions look like. This is what ChatGPT is, this very elaborate looking neural network we'll see on Tuesday. And it has a ton of weights. It actually has like I don't know how much the most recent ones, but like they have in the hundreds of billions of weight, like numbers, these weight vectors. So it's incredible how many, but all they're doing is just trying to decide what each one should equal such that it just outputs what's going to be the next word. Okay. Maybe that's all I say. But yeah, this activation function thing, like you should be confused what it is because I haven't told you what it is. But it turns out there's all sorts of choices, and we're not going to get into the details of it. Okay, let's get into the most general case of what this neural network looks like. So in general, it looks like this, and I've kind of alluded to this, which is it doesn't need to have like 2 or 3 layers. It can have as many layers as you want. We'll call that variable B. And the reason I don't use L is because we've always used that for the expected loss, and that would be very confusing. B layers, you can think of it like B blocks or something like that. One thing to notice that we've seen in the past example is that the last layer does not have a bias term. This should make sense because the last layer hasn't, like it's not multiplying anything. There's no weights multiplying it or anything after. And the last layer can have multiple outputs. Each of these, so you can output many, many things. You can output whatever, like as many things as you want. And you can think of this as maybe like predicting the probability of a cat, a dog, an elephant, a lion, and so on and so on. And we've seen this in the multi-class classification case. And there's a reason I haven't talked about softmax yet. And if we have time, I'll talk about it at the end, but we'll see if we have time. But it will be in the course notes. But it turns out softmax is not exactly a neural network. Like you can't exactly represent it by a neural network. But all you have to do is just like apply one extra step at the end. And there's a reason, but I don't want to, it's like kind of a technical mathematical detail. But yeah, so you should really think of this as being very similar to what softmax was doing. You can output many possible, a vector of outputs, potentially representing like the probability of one class or second class or third class in classification. Or like in regression, well, yeah, in regression actually, it's exactly representing the probability of the first and whatever. That would be the softmax regression setting. Yeah, so anyways, each one of these layers has like d to the power of like, let's say 1 neurons here, there's d to the power of b minus 1 neurons here, there's d to the power of b. Okay, so now what we're going to do is write out what are all the things in this network and how are they defined in the general way. So we've done it in like the case before for the very specific network we saw. Now we're going to do it for this general one. And so we're going to just do it for a single layer because all of them are kind of like almost the same. So for some layer, and we're going to use a variable for layer B that's an element of layers 1 up to capital B. We have the following kind of expressions or terms and whatever in terminology. So there is these things called the weights in the network, right? We've seen these. So what are all the weights? If we look at a single layer, there's a certain amount of weights. It would be all of these connections. These are all the weights for layer 1. There's some amount of connections for layer 2 up to layer B minus 1. There's a bunch of weights. And then for layer B, there's also these weights. So every layer has its weights. There's many weight vectors at every layer. So we're focusing on just one layer. What are the weights there? Well, so we're at layer B, that's the superscript. The subscript just indicates this is the weights for activation 1. Then there are weights for activation 2 at the same layer, up to weights for activation. Okay, so layer B. Okay, so now what should the subscript here be? So let's say we're at let's look at layer 1. So there's some weights for activation 1, then there were some weights for activation 2. We get to the bottom, we need weights for activation. What is this index? It's the dimension, it's the how many activations are there, and the variable I'll use here is D to the superscript of the layer. So hopefully that should make some sense. Is now I should have D to the superscript of 1. So this is the number of activations at the first layer. So so as many as there is of these, you need that many weight vectors. Each one has like this weight vector connected to every previous neuron, right? This one's connected to every previous neuron and so on. So a lot of weight vectors. Okay, what is the dimension of each one of these? Each one of these, right, has to connect and apply, there needs to be a dot product applied to the previous layer. So they should be the same dimension as the previous layer. So that would be D of dimension B minus 1. Oh, sorry, there's one thing. So this 1 here should be B, right? Because we're looking at dimension B. I was just saying that we focus on the layer 1 case to get an idea of what it is. Yeah, back to the dimension of the weights. So the weights should be the same dimension as the previous layer because they're dot producting the previous layer. Plus 1, because they also dot product with the bias. Those are the weights. What are the weights used for? They're used to calculate pre-activations. These are the Z's. How many of them is there at a layer? What are their dimensions? That's what we do next. So you can think there's a vector of them. Just like there's a vector of activations at a layer, there's going to be a vector of these. Each one of the indices is going to be passed into the activation. So you have ZB of 1 up to Z, so at this layer B. And then here, once again, we use D of B. There should be as many pre-activations as there is activations. What is the dimension of each one of these? Well, each one is just a number. It's a dot product. How many is there? There's 1 till D of B. So there's D of B of them. So this vector is an element of R of D of B. Okay. I'm really emphasizing this is like kind of maybe the most important thing when you work with neural networks is like matching dimensions of objects and making sure they match. And this gives you a lot of intuition about what's feeding into what and what not. So that's why I'm really stressing the dimensions of things. Okay. What is each one of these pre-activations defined as? Well, it's just the dot product. So each one of these, so for some index J, is equal to the dot product of the previous layer's activation vector. So that would be A of B minus 1, right? That's a vector. Dot producted with the weights for the current layer for the jth activation. Current layer B, jth activation. Okay. And this is, of course, for, like I just wrote it for a specific J, but this holds for like all of these, like 1, 2, up to DB. Okay. That's the pre-activations. Of course, these pre-activations are then passed into activations. So these are the things you see in the picture. The activations are the values of the neurons. So you can think of the neurons as doing this calculation, right? Which is to take a dot product, apply an activation function, and then the output is the activation. That's what the neuron does. And maybe the thing I should have said is this is somewhat inspired by this like biological idea that you have each one of your neurons like takes some input, which is like that has, what is it, the dendrites or something. They like connect to other neurons, they take in inputs, they do some processing, then they output a signal of like on or off kind of, which is how you should interpret this. Okay, finally, the activations. And here there's some special cases you need to look at. So first of all, the very first, the 0th activation is the input. And this has no calculation, it's just the input. Right, so this vector is just x, it's just the input feature. That's of a dimension r of d plus 1. So that's like a special case, and like we'll use the notation r of d0, which is like the dimension of the 0th layer as well. So here d0 equals to d. Okay. There's another special case, which is the last layer. Why is that a special case? Well, that's because the last layer doesn't have a bias term. It doesn't need the bias term because there's no other layer in the future that's going to be using it by multiplying with weights. The only reason you needed this bias, like for instance, like here, is just so that the new, like the activations at this layer can then use it as an offset when it does this dot product thing. As like this y-intercept kind of thing. Okay, so the other special case is A activation at the final layer B. Okay, so that thing is going to just be one less dimensional than all the other layers. So it's going to have A1. So yeah, the important thing is it starts at A1 here. Up to A of dB, which is the dimension of that activation vector. Okay. So that's what this guy is. What is its dimension? Like, where does it belong to? It belongs to R of dB, of course. This is literally the definition of D of B. It's the dimension of the activation vector at the bth layer. Okay, and now here we have the every other layer. So for B, yeah, all the other B's. So not including capital B and not including 0. It has this special bias activation, always equal to 1. And then, oh, this is the 0th index. And then all the others will have a definition, which is based on the activation function. Okay, D of B. B. Okay, there definitely should not be a superscript 0. We are at layer B. And what is the dimension of this? Well, it's almost the same as the one above. It has this D of B, but now it has this +1 for the bias. Just the dimension of the activation vector, +1 for the bias. Okay, what is the definition of these? Quite simple. It's like we've seen before. So the activation at layer B of activation J is equal to an activation function H applied to the dot product, this linear function Z, which we've defined above, which is called the pre-activation. And the pre-activation at layer B, index J. Okay, and this is for J again, for all of the indices at that layer. So 1, 2, how many activations there are at the layer D of B. Okay, so this is really the whole, like this is all the terms in this neural network. So what is the, okay, maybe one more thing that I wanted to define, which is there's this activation function that was used, H, right? First, like this activation function is just going to be a function from reals to reals. So that's all you really need to know. This thing does not map to vectors or anything. It's just like takes a real number, maps to a real number. For instance, the sigmoid, it took a real number, mapped to a real number. It actually mapped it between 0 and 1, but that's of course a subset of the reals. Yeah, so there's all sorts of different activations. There's, maybe I give you some terms. So there's the sigmoid. Another classic one is this thing called the rectified linear unit, and people call it the ReLU. The one used in GPT is this thing called the Gaussian error linear unit, the GELU. And there's more than enough of this fun and research done into these. But these change a lot of things for different reasons, which we won't talk about. Okay, what did we get to with all this? What we got to is that we have a neural network. What does the neural network look like? The neural network is the following. It's a function that takes in as input x, passes it through all of these layers. Each of these activations depends, so let's just look at one thing. Like each one of these activations depends on the pre-activation. Each pre-activation then depends on the previous layer's activation, and then that activation depends on the previous layers, or the pre-activation, which depends on the layer before that's activation, and so on and so on. So there's like this whole backwards thing that goes all the way back to the input. And so what we will write is that the neural network just outputs the activation vector, right? So the neural network will output a vector of things. It can be output a vector of, let's say, probabilities at the bth layer. So that's a neural network. So that's our definition. And I want to, yeah, so that's that. Okay. So it's just like a bunch of these things applied over and over and over again. And I'm going to define it in like a matrix version, which makes it a lot more clear how these things are being chained together. And you'll also see why the activations are important from that definition. Let me finish this lecture, and then maybe I can take the lectures after class, because I really want to finish these last things. Okay, so important thing, which is there's a lot of things you need to define a neural network, right? There's like, how many neurons do you have? How many layers do you have? What's like, what activation do you use? What are the weights, and so on. So it turns out that if you define a specific subset of these things, which should make some sense, which is if you define the number of layers, right? If you define the number of layers, you can already see, you can kind of draw the neural network. You know how many of these like vertical columns there's going to be. So if you define the number of layers, and then if you define and the number of neurons in each layer, oh, that's an interesting spelling, in each layer, what are these variables? These variables are dimension of layer 0, which is just D, dimension of layer 1, up to dimension of layer B, last layer. If you decide on some values of this, and the activation, so if you define you choose an activation, all that's left, okay, so you choose an activation H, all that's left is actually just to define the weights. But if you don't choose values for the weights yet, which is going to be the thing you're actually optimizing over, this is called defining. So this whole thing defines what is called a neural network architecture. So you will hear sometimes people saying, like, these big companies, they'll release the neural network. Like, there's two things that you need to run like this function. You need the neural network architecture, and then what's missing here is the weights. If you then know the weights, you can then actually calculate everything. Okay? So usually what people will not release is the weights of these, like, or sorry, they'll release just the weights, but they won't release like this whole neural network architecture and so on. Or they'll release one or the other and whatever. Yeah, that's all but like, these are two different things. Okay, maybe the more important thing to point out here is that the neural network architecture really defines a specific function. And if you change the weights, you get different functions. What you're going to try to do is optimize or find the best weights to solve your problem or to do the prediction stuff. And now before I define this, like, how does ERM look and what does it mean to optimize over the weights, I define one more thing, which is this matrix notation, which should make the neural network kind of definition look a little bit cleaner. Which is, you might notice at each layer B, we have a bunch of weight vectors. Actually, D to the B, which is the number of activations there, number of weight vectors. You can stack these all into a matrix as column vectors. Like this, right? Now you have a matrix of weight vectors. The dimension of this guy is D of B minus 1 plus 1 by D of B. Okay, so that's the dimension. The reason why is each one of these guys is of dimension the previous activation vector's dimension, plus 1 for the bias, times the number of columns there is. What's the point of this? The point of this is that you can rewrite the activation vector not as its elements, but as just an operation, which is the following, which is the activation vector of the previous layer transpose applied not to a vector now, but to the whole matrix. So this is the above matrix. And now this H is taking as input a vector, and what that means, and you can look at the lecture notes, but this is applied element-wise. So I said that H was like a function from reals to reals, like numbers to numbers. Well, if it takes in a vector, then it just applies it to each vector one by one. So you have this compressed picture. But what I really want to emphasize is now you can write the neural network as follows, which is this function, right? It was just the last activation vector. We've seen this. What does it look like with this notation? Well, it looks like this giant kind of onion of operations. So you have the very first, so you have, okay, all right, let's start like this. You have the feature vector, right? That starts as the input. What happens to that feature vector? You apply transpose, and you apply this linear function with the weight matrix for the first layer. You then apply the activation function to this thing that's called the pre-activation to now get the activation, right? This is the activation vector for layer 1. What do you do with that thing? You then, it turns out this, okay, so this thing will be a row vector because this is applied element-wise, and if you look at the dimensions, so you don't need a transpose is all I'm trying to say. You then take the linear function with the next layer's weight vectors, so this would be this weight matrix, and then you apply an activation function on that. This is the activation vector at the second layer. And then you can do this all the way onwards. There's going to be like the weight matrix at layer B minus 1, and then the weight matrix at layer B, and the whole thing transposed because it's a vector. And then you have activation. Okay. So this is what I want you to see. Is you start with this vector, you then apply the linear function, you apply an activation. You apply the linear function, you apply the activation function. And then you keep doing that until the end, and you have this giant chain of operations doing the same thing over and over and over again. And what you will find is that if you change h to just be the identity function, all these h's can go away. They just output what they've been input. And what you'll find is that this whole thing looks like x times a matrix times a matrix times a matrix times a matrix. And that whole thing, what's a matrix times a bunch of matrices? That's just another matrix. You can just call that your linear function. So you end up with something that's just a linear function. So if you remove the activations, you really get nothing but a linear function. Okay. And then maybe, yeah, there's 2 more things to kind of end, but it's all written up, so this is great. So it should be quite straightforward. Like at the end of the day, all we've done is changed our function class to neural networks. And how you would properly write this is you would now say your function class are neural networks with a specific architecture. So you like fix the architecture. You say like, oh, I have this many layers. This is why this is so important. This many layers, this many neurons in each layers, and I use this activation function. All that's left now is weights. That's the only thing that changes functions apart from each other in this neural network architecture. And what you're now doing, like the important note, is that each one of these functions inside this function class, I subscript them by their weight matrices. They are exactly defined if you just define their weight matrices. Once you have this, you have perfectly defined the neural network. And so you can think of then your learner, which is minimizing this estimated loss, right? It's outputting f hat. F hat is the output of the neural network. But what is that, like, how do you define this guy? Well, it's defined by all of these weight matrices, right? And what are these weight matrices? They're just the ones that minimize the estimated loss. And the estimated loss, what is that? That's like you have this loss function that takes in a predictor and a true label. And now your predictor is just fully described by these weights. So you're really just searching over a giant set of weight vectors. In softmax, we've seen how you can search over many weight vectors. Here you have like even more weight vectors. You have all these weight vectors for each layer, and then you have multiple weight vectors at each layer as well. So you have B weight matrices. And so the whole search of all this neural network stuff is searching over these giant weight matrices. And when you finish training a model, which is like you've optimized the model and so on, you then output some set of weights, and then you have your predictor. Okay. And the last maybe there's 3 things to just very quickly note. Okay, so it turns out that when you use these neural networks, you then run into the first problem, which we've seen before, usually no closed form solution. So that says we must use gradient descent. That's this equation below. The equation's super, like it's as everything we've seen before. You just take the gradient of the loss. But similar to softmax, we're doing it for every single weight vector. So the bth weight vector and the jth index in there. So that's what you would do. And the other thing to note is that it actually turns out that usually things are not convex. Okay, and what that means is if you were to draw like your estimated loss in one dimension, you don't have a smooth looking, like convex looking bowl shaped thing, but you have a thing with multiple kind of minimums. And so neural networks will usually find these like local minimums. And it turns out that this actually still somehow is good, and we won't go into all this stuff in this course. But this is the first time we see this non-convexity, and why we haven't really covered neural networks till now. They really face this non-convexity problem. Okay, and then the final thing, which I won't say, is that softmax can be thought of as a neural network, but you have to apply this, like, it's just a neural network, but then you apply one more step, which is like you apply the softmax function to the output, and it'll be in the course notes and stuff. Okay, that's it for today. Thank you.